Hello everyone, my name is Nidhi Chauhan. I am assistant professor in Gyan School of Pharmacy, which is a part of the Suresh Gyan University, Jaipur. And today we are going to discuss the polynuclear hydrocarbons, which comes in your fourth unit, your pharmaceutical organic chemistry, and uh, and the learning objective. And the learning objective of this topic is about the polynuclear hydrocarbons. That what are the polynuclear hydrocarbons, which we also known as the polyaromatic hydrocarbons, and also we are going to study about the naphthalene, its isolation, and its and also learn about the resonance structure, its method of preparation, and the student outcome. There they are going to know about what are the polynuclear hydrocarbon or your polyaromatic hydrocarbons. They will also going to know about the structure of the naphthalene, what is the structure of naphthalene, how it is isolated, and what are the resonance structure of the naphthalene, and its method of preparation as well as its chemical reaction also. The students will going to know. So now polycyclic aromatic compound or your polynucleic hydrocarbons or your polyaromatic hydrocarbons are the compound which are having two or more fused benzene ring in their chemical structure. It means this polycyclic and aromatic hydrocarbons are having the benzene rings that are fused with benzene ring is one, and it is fused with two benzene ring or with the three benzene ring or more than more benzene that are fused in their chemical structure, and there is no presence of heteroatoms and substituents on the polycyclic ring. So there is no presence of heteroatoms. Heteroatoms like nitrogen, sulfur, oxygen. These are the heteroatoms. So there will be no presence of your heteroatom on these polycyclic aromatic hydrocarbon and substituent on the polycyclic ring, as well as there are no substituent on this polycyclic ring. PAH were first discovered. PAH is a polycyclic aromatic hydrocarbon or a polynuclear hydrocarbon. They were first discovered in Coal in the 19th century and have become one of the widely investigated compound in medical science, biology, and organic chemistry in recent years. So here, these polycyclic aromatic compounds are the compounds that are having two or more fused benzene ring in their chemical structure, and they are also there is no presence of heteroatoms. So there are no heteroatoms are not present on this fused benzene ring or on the substituent in on the and there is also no presence of the substituent on the polycyclic ring, and this polyaromatic hydrocarbons, they were first discovered from this coal tar and in the 19th century. In the 19th century, this PAH was discovered. PAHs were discovered and from this coal tar, and they have become one of the widely investigated product compound in the field of your medical science, biology, and the organic chemistry. So polyaromatic hydrocarbons are considered as a main carcinogen before the 1950. So before this 1950, they were considered as the main carcinogen. I mean, they are cancer-causing agents. This PAH, it was believed that these PAH are causing cancers, and nowadays PAH is still one of the most important classes of carcinogen due to their abundance in the environment. So these PAH are present in the environment in the abundant amount. So these are they are the most important classes of carcinogens. So PAH with four rings are called light PAH, whereas those containing more than four rings are termed as heavy PAH. Means the polycyclic aromatic hydrocarbons in which the four benzene ring are fused. They are known as light polycyclic aromatic hydrocarbon, whereas they are having more than four rings. In more than four rings, which of the benzene rings are fused, then they are known as your or heavy polycyclic aromatic hydrocarbon. So heavy PAHs are more stable and more toxic as compared to light PAH. So these heavy polycyclic aromatic hydrocarbons, which are containing more than four rings, they are more stable. They are more stable, more toxic as compared as they are compared to this light PAH. Similarly, the increase in the size and angularity of the PAH molecule result in the increase in hydrophobicity and electrochemical stability. So if there is an increase in the size and the angularity in this pH molecule, this can also increases the hydrophobicity and electrochemical stability in this pH molecules. Hydrophobicity means they are not soluble in the water because and there is an electrochemical stability. It means both of these things are increases in this if the size and the angularity of a pH molecule increases. The delocalization for the of electrons on the polycyclic aromatic structure is responsible for the electronic and optical properties of pH. So these, if there is a delocalization of electron on the polycyclic aromatic structure, then they are responsible for the electrons and optical properties of PAH, and ring linkage pattern in PAH may also occur in such a way that the tertiary carbon atoms are centers of two or three interlinked rings. So here this ring linkage pattern, the ring linkage pattern present in this polycyclic aromatic hydrocarbon, they are occurred in such a way that the tertiary carbon atoms at the center of the two or three interlinked rings. These links which are interlinked in this, the tertiary carbon atoms are present in the center of this. Again, these polycyclic aromatic hydrocarbons are the compounds with two or more fused benzene ring in their chemical structure. These polycyclic aromatic hydrocarbons, these are the compounds, these are the hydrocarbons, they are having two or more fused rings. These benzene rings are fused or uh, fused two benzene ring, either two benzene ring are fused or three benzene ring are fused, or more than this two or three benzene rings are fused in their chemical structure, and there is no presence of the heterocyclic, there is no presence of the heteroatoms on this fused benzene ring, as well as there is no presence of the substituent on this polycyclic ring. And this PAH were discovered in coal tar in the 19th century. So in the 19th century, this PAH, this polycyclic aromatic compounds, has been discovered and from this coal tar, and have become one of the widely investigated compounds. So they are become the widely investigated compound in the field of medical science, biology, and your chemistry in the recent year. So here the PAH were considered as the main carcinogen. So this PAH before 1950s, they were considered as the carcinogen. They have the carcinogen effect and they are the main carcinogens. And nowadays PH also still considered as the carcinogen because they um, have the property of this carcinogen in them, and there is also presence of this and they are also present in abundant amount in the environment. So this PAH with four rings, the four rings that are fused in this four benzene rings are fused in this PAH, that is a polycyclic aromatic hydrocarbon. They are known as your light pH, and these more than four benzene rings that are fused, they are known as heavy PAH. So here the heavy PAH are more stable, they are more stable and more toxic They are more stable and more toxic as compared to the or light pH. So these heavy pH are more toxic and more stable and more toxic as compared to your light pH. So similarly, if the size and angularity in this PAH molecule result in the increase in the hydrophobicity and the electrochemical stability. So this, the delocalization of electron on the polycyclic aromatic structure is responsible for the electronic and optical properties of this PAH. So the delocalization on this PAH molecule, delocalization of electron on this PAH molecule, this PAH, this polycyclic aromatic structure on this polycyclic aromatic structure is responsible for the having this electron and this optical properties in this PAH. And the ring linkage pattern in this PAH may occur in such a way that this ring linkage occurs in such a way that the tertiary carbon is present in the center of the two or three interlinked rings. Next is your nuclear hydrocarbons. A polynuclear aromatic hydrocarbon is a hydrocarbon that are made up of fused aromatic ring molecules, and these rings share one or more side and contain delocalized electrons. So these polynuclear aromatic hydrocarbons are the hydrocarbons that are made up of your fused aromatic rings. That aromatic rings means benzene rings are fused. So these rings share one or more side and contain delocalized electrons. So these rings which are fused to form a polynuclear aromatic hydrocarbon, they share one or more side to the another ring, and they are also containing the delocalized electrons. So another way to consider PAH is molecule made by fusing two or more benzene rings. Polynuclear aromatic hydrocarbon molecule contain one only carbon and hydrogen atoms. So this PAH is molecule. They are made up of fusing two or more benzene, or they are made up of fuses to aromatic ring molecule, and they are sharing one or more side, and they are containing delocalized electrons. And the polynuclear aromatic hydrocarbon, these molecules contain only carbon and hydrogen. As I have told earlier in the last slide, that there is an absence of heteroatoms as well as um, heteroatoms, and the substituents are absent on this polynuclear hydrocarbon. So they are formed by the two or more benzene rings which are fused, and their polynuclear aromatic compounds, they are containing only carbon and hydrogen atoms. So the properties of this polynuclear hydrocarbon is that the polynuclear aromatic hydrocarbon are lipophilic, means they are soluble in the lipids, they are non-polar molecules, they tend to persist in the environment because PAH are not very soluble in water, while 2 and 3 ring PAH are somewhat soluble in aqueous solution. The solubility decreases nearly logarithmically as molecular mass increases. 2, 3, and 4 ring PAH are sufficiently volatile to exist in the gas phase, while larger molecules exist as solid. Pure solid pH may be colorless, white, pale yellow, or pale green color. So the properties of this, or the you can say the physical properties of this polynuclear hydrocarbon is that they are lipophilic, means they are soluble in the lipid loving. and they are non-polar molecules. These are non-polar molecules. Their polarity is not present in these molecules. They tend to persist in the environment. They are persisting in the environment because pH are not very soluble in water. So these are not soluble in water, but they are soluble in the organic solvents. While two and three rings of this pH are somewhat soluble in aqueous solution. But these uh, polynuclear hydrocarbons, which are having two or three rings, they are fused. They are soluble in your aqueous solution, and the solubility decreases. The solubility of this aqueous solution in the aqueous solution decreases as the molecular mass, as their molecular mass is increasing. As their molecular mass is increasing, this solubility decreases. The 2, 3, and 4 ring PAH, the 2, 3, and 4 ring of the PAH are sufficiently volatile. Uh, these rings, these containing 2, 3, and 4 rings are volatile, and they are existing in the gas phase. So they are acting as a gas phase. So they are present in the nature as a gas phase, which are containing 2, 3, 4 rings, and they are volatile in nature, and they exist as a gas gas state. So while larger molecule exists as solid, but the larger molecule that are fused, they are exist as a solid, and the uh, pure solid pH, the polynuclear aromatic hydrocarbons, which are solid, they are colorless, they are white colored, they are pale, they are yellow, or they exist in the pale green color. So these are the polynuclear hydrocarbons which are formed from the fused ring of two or three benzene ring. And secondly, they are lipophilic and non-polar molecule, but they are two three rings of this pH are soluble in aqueous solution. As there is a decrease in the molecular mass, are they as the solubility decreases, as the molecular mass increases, and they exist in the gas phase, the 2, 3, and 4 fused ring of the pH, and they are who they are having, whom have the pH which are having 2, 3, or 4 rings. They are volatile and they exist in the gas state. And while the larger polyaromatic hydrocarbons, they are exist as solid. So these solids are colorless, white, pale, yellow, or green color, pale green color. Next, sources of this PAH. So PAH are organic molecule that forms from a variety of natural and environmental pollutant reaction. So the reaction that is due to the environmental pollutant, so they forms this PAH molecule. So the natural PAH forms from forest fire and volcanic eruption. So when there is any volcanic eruption, that means there is a formation of this PAH hydrocarbon, that is your polynuclear aromatic hydrocarbon. And they are also formed from the exist in forest fire also. When there is a fire in the forest, then this natural PAH are formed from that forest fire. So the compounds are numerous in fossil fuels such as coal and petroleum. So these are present in numerous amount in the fossil fuels, that is your coal and petroleum. And man contributes PAH by burning wood and by incomplete combustion of fossil fuel. Means if there is an incomplete combustion of this fossil fuels, means your coal and petroleum, then there is a liberation of this PAH. And also, if men's are burning woods, then there is a contribution. They are contributing this PAH in the environment. So the compound occur as a natural consequence of cooking food, particularly when food is cooked at a high temperature, grilled or smoked. The chemical are released in cigarette smoke and from burning waste also. So these compounds, they are also occur from this cooking food, when the food is cooked at a high temperature, if the food is grilled or it is smoked, then this pH are evolved from there. And the chemicals are also released. These PAH, that is the polynuclear aromatic hydrocarbons, they are also released from this cigarette smoke and as well as from the burning waste. So these PAH are the organic molecules. These PAH are the organic molecules that are formed from a variety of natural and environmental pollutant reaction. If there is a reaction that is happening in the natural and the environment pollutant, then there is a formation of this PAH organic molecule. So this natural PAH, these are formed from the forest fires as well as from the volcanic eruption. So these compounds are present in numerous amount in the fossil fuels, that is your coal and petroleum. And the man can contribute PAH by burning wood. So the mans are contributing this PAH by burning woods and by the incomplete combustion of fossil fuels. The compound occurs as a natural consequences of cooking food, and when food is cooked at a high temperature or grilled or smoked. So from there also this pH is evolved out, or there also the pH is formed. The chemical are also released in the cigarette smoke and from the burning waste of. So health effects. The health effect of this PAH is that they are extremely important. This PAH aromatic hydrocarbons are extremely important because they are associated with genetic damage and diseases. So they are causing, or they are associated with this genetic damage as well as with the diseases, and also the compound persists in the environment leading to increased problem over time. And this PAH are toxic to aquatic life also, to the water life also, the living organism that are present in the aquatic, or you can say the aquatic organism also. So these PAH are toxic to this aquatic organism also, or to the aquatic life. In addition to toxicity, these compounds are often mutagenic, carcinogenic, and teratogenic. And the prenatal exposure to this chemical is associated with lower IQ and childhood asthma. So, if the prenatal exposure, if there is an exposure to this exposure to the prenatal, then this chemical can cause the low IQ and the asthma also in the childhood. And these are toxic to the aquatic life, and these compounds are also mutagenic and carcinogenic and teratogenic. People get exposed to PAH from breathing contaminated air, eating foods that contain the compounds, and these that people get exposed. People are exposed to this PAH, that polynuclear aromatic hydrocarbon, by breathing, when they breathe from contaminated air, and also eat food that contains the compound, and from skin contact also, the people get exposed. And unless a person working in an industrial setting, with these chemical exposure tends to be long term and low level. So there aren't medical treatment to address the effect. The best defense against health effect from PAH exposure is to become aware of situation that elevate risk, breathing smoke, eating charred meat, and touching petroleum products. So if there is no medical treatment against this effect of this polynuclear aromatic hydrocarbon, so the best defense against this health effect from this pH exposure is to become aware from this PAH compounds, and these can also elevate a risk of breathing smoke, eating charred meat, and touching petroleum. We should not touch the petroleum products, not eat the charred meat, and also do not breathe the smoke. So these polynuclear hydrocarbons are extremely important because they are associated with the genetic damage as well as the disease, and also the compound persists in the environment leading to the increased problem over time, and these are toxic to aquatic life, and these are also toxic These compounds are also mutagenic, carcinogenic, and tetragenic. And prenatal exposure to this chemical are causing the low IQ and the childhood asthma also. If people get exposed to this PAH from breathing contaminated air, then eating food contain the compound, and from skin contact, unless a person works in an industrial setting with these chemical exposure, tend to be long term and low level. So there aren't medical treatment to address the effect. So the best defense against health effect from PAH exposure is to become uh, aware of situations that elevate this risk of breathing smoke, eating charred meat, and your touching petroleum products. Next, this is the classification of the polynuclear hydrocarbons. So these are divided into two classes, that is your benzenoid, and second is your non-benzenoid. So in your benzenoid, you will see this is your azulene structure, and this benzenoid is again divided into two types, that is your isolated and the fused ring. So this isolated example is your biphenyl, and the fused ring is again divided into two structures, that is your linear and your angular. So this linear example is your naphthalene, and this angular example is your phenanthroline. So this polynuclear hydrocarbon is divided into two categories, that is your benzenoid, and second is your non-benzenoid. So here, this benzenoid is divided into two structure two categories. Again, it is divided into two categories, that is your isolated or fused ring, and this isolated example is your biphenyl, and the fused ring is again divided into two class, that is your linear and your angular. So this linear example is your naphthalene, and your angular example is your phenanthroline. So naphthalene chemical formula is your C10H8. So the carbon that is present in this naphthalene are 10 and H8. So it is an aromatic. Um, it is an aromatic. It is an aromatic hydrocarbon in which two benzene rings are fused in ortho position. For the purpose of naming its derivative, the position are indicated by figure. So here you can see that this is having this carbon 10 and hydrogen 8, and this is an aromatic hydrocarbon, and in this two benzene rings are fused in your ortho position, and the purpose of the naming is derivative. The position are indicated by figure. So here you can see this is your naphthalene structure, and here you will count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So carbons are 10, and two benzene rings are fused fused in a ortho position. Ortho, this is your ortho, and this is meta. So it is fused in your ortho position, and the hydrogen that is present in this naphthalene is your, you can count here, 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens are there in this naphthalene ring. So here double bonds are present on this portion, and here this carbon is not having any hydrogen because it is already bonded to four sides. So here 2, 3, 4, and 1, 2, 3, 4. So both of these carbons are bonded to the four side. That is why they are not having any hydrogen present on this. And these carbon, that is your this carbon is having one hydrogen because 1, 2, 3, 4. These are bonded to one side hydrogen, and two side the carbon is bonded to the two side of the carbon. So isolation from coal tar. So this naphthalene is the largest single product component of coal tar absolute, that is 6 to 10%, and the hydrocarbon was first noticed as a deposit in the condenser during the distillation of naphtha fraction, and hence its name. It is obtained chiefly by cooling the middle oil fraction and 160 to 200 degree, and whereupon naphthalene crystallizes out, the crude crystals are removed by centrifuging. So here the naphthalene is the largest single component that is present in the coal tar, about 6 to 10%. So about 6 to 10% in coal tar there is the presence of this naphthalene, and this naphthalene was first noticed when there is a deposit of this naphthalene in the condenser during the distillation when there was a distillation of this naphtha fraction was occurring, and there is a deposition of this naphthalene occur, this hydrocarbon occur in the condenser. At that time it was first noticed, and hence it was named according to naphtha. These are obtained from the naphtha fraction, that is why it is named naphthalene, and it is obtained chiefly by cooling the middle oil fraction. So these are obtained by cooling the middle oil fraction at 160 to 200 degrees centigrade. Where upon naphthalene crystallizes out, where at 160 to 200 degrees centigrade to 50 degrees centigrade, the naphthalene gets crystallized out. The crude crystals, these crude crystals are removed. These are removed by centrifuging. So these are removed by centrifuging. These are melted and then treated successfully with the concentrated sulfuric acid to remove phenol. So these crystals which are removed by the centrifugation. These are melted and then they are treated with your concentrated sulfuric acid so that we can remove phenol from it. Finally, the naphthalene is sublimed to give the pure product. So this naphthalene is sublimed to give the pure product. So which the naphthalene that is formed from this melted and solid, this naphthalene is melted and then it is treated with concentrated sulfuric acid for the removal of the phenol part from this naphthalene, and this naphthalene is sublimed to give the pure product. So the physical property. So physically, naphthalene is a white solid which crystals in shining plates. This is a white solid. Its color is white solid, and its state is solid. So its color is white. So it is a white solid that is crystallizes in shining plates, and its melting point is minus 80 degrees centigrade, and its boiling point is to 18 degrees centigrade. They have a very strong odor and they are very volatile. They sublime readily on warming. So when we warm it, they sublime it, and naphthalene is insoluble in water. So these are insoluble in water and they dissolve easily in your organic solvents, and particularly these are dissolved easily in your ethers and your benzene. So here the whole these naphthalenes are the first largest single component that has been isolated from this coal tar, and as that are present in the coal tar about 6 to 10%. And this was first deposited in the condenser during the distillation of the naphtha fraction, and after that it was named by this naphthalene, and it was obtained chiefly by the cooling of the middle oil fraction, and thereon naphthalene crystallizes out, from where the naphthalene is crystallizes out, and these crude crystals, these are removed by a centrifuging, and these are melted and these are treated successfully with the concentrated sulfuric acid, and so that they can remove phenol from it, and finally the naphthalene is sublimed and they give the pure product. Next is the properties. So these properties of the naphthalene is that it is a white color solid. It is present in solid state and which crystallizes in shining plates, and which forms crystals. It is having a crystal and its melting point is minus 80 degrees centigrade, and its boiling point is 210 degrees centigrade to 18 degrees centigrade, and it is having a strong odor. The smell of this naphthalene is strong and it is very volatile and sublimes readily on warming. So here, if we warm it, then it is converted into the vapors. So here, naphthalene is your insoluble in water. This naphthalene is your insoluble in water and it dissolves in your organic solvent, especially or particularly in your ethers and your benzene. Next, chemical. The reaction of naphthalene are essential, the same as that of benzene. It also undergoes substitution readily and form addition products. However, it is somewhat less aromatic than benzene. Thus, the double bond in naphthalene exhibit in part of the reactivity of alkene, and it forms addition compounds more readily than does benzene. As soon as one of the ring is fully saturated by addition of hydrogen or halogen. So the chemical property of this naphthalene is that the reaction of this naphthalene is same as that of your benzene. It also undergoes your substitution and it gives you addition product, but it is less aromatic than your benzene, and the double bond that is present in the naphthalene that exhibit the reactivity part of the reactivity of the alkene, and it forms addition compounds more readily than does benzene. And if the whole of the ring is fully saturated by addition by the addition of hydrogen or halogen. So the resonance structure of your naphthalene. So X-ray diffraction. After the X-ray diffraction studies shows that unlike benzene, all carbon-carbon bond in naphthalene are not of the same length. So in case of this carbon-carbon bonding in naphthalene, they are not of the same length, and in particularly the C1 C2 bond is considerably shorter, 1.36 angstrom, and then the C2 X3 bond, that is your 1.40 angstrom, and this difference can be understood if we examine the three resonance form given below. Notice that the C1 C2 bond is double in two structure A and B, and single is only one C. So here this is your A and B, and here it is written here that the difference can be understood if we examine the three resonance here in the A and B. You will see the double bond in two structure and single in only one. You can see here the double bond in A and B, and here it is single in one. So here you will see the one having this C1 and C2 is having the double bond, and C is having the single bond. So here, whereas C2 and C3 bonding single in two structure and double in only one C. So here this C2 and C3, here they are the single structure in C2 and C3, A and B. But in case of C3, in case of the C, there is a double bond present. So here, whereas at C2 single in two structure and double in only one. So we would therefore expect that C1 and C2 double bonds to have more double bond character, shorter bond length, and C2 and C3 bond to have more single bond character. So here, X-ray diffraction study shows that unlike benzene or carbon-carbon bonds in naphthalene are not the same length. When particularly the C1 C2 bond is considerably shorter, and then the C2 C3 bond, that is your 1.440 angstrom. So the difference can be understood if we examine the three resonance forms. So in this resonance form, you will see in the A and B structure, the C1 and C2 is having a double bond, and in C, this is C1 and C2 are the single bond. So whereas in C2 and C3 bond is single in two structure and double in only one C. So we would expect that the C1 and C2 bonds are having a more double bond character, and which is having the shorter bond length. And the C2 and C3 is having a more single bond character, and this is having a longer bond length. So the resonance structure of naphthalene is about 61 kilocalorie per mole. The energy that is the resonance energy of this naphthalene is your 61 kilocalorie per mole, and this value is less than twice the amount of a single benzene ring. So the value that is less than twice the amount of a single benzene ring, that is 36 kilocalorie per mole. So as a result, naphthalene is somewhat less aromatic than benzene. So as a result, this naphthalene that is less aromatic than the benzene structure. Less aromatic, more reactive than benzene. So the preparation of naphthalene. So here from 3-benzoyl propanoic acid, when 3-benzoyl propanoic acid is heated with sulfuric acid, alpha naphthol is formed, which on distillation with zinc amalgam or zinc dust form naphthalene. So this benzoyl propanoic acid, when it is treated with this benzoyl, when it is treated heated with the sulfuric acid, there is a formation of this alpha naphthol is formed. So this alpha naphthol is formed, which is then in the presence of this zinc dust, and there is a formation of this naphthalene is formed. So this is the first method of preparation of this naphthalene, from where this naphthalene is prepared from this 3-benzoyl propanoic acid. From this propanoic acid, there is a formation of the alpha naphthol, and this after that this is distilled with the zinc dust, and there is a formation of a naphthalene. Next, it is from 4-phenyl-1-butene. So from here, 4-phenyl-1-butene is passed over red hot calcium oxide, naphthalene is formed. So this 4-phenyl-1-butene is passed over the red hot calcium oxide, and there is a formation of this naphthalene plus hydrogen gas is dissolved out. Secondly, Howard reaction synthesis. So Howard synthesis, it involves 5 steps. In this, the formation of 3-benzene propanoic acid by the treatment of benzene with succinic anhydride. So benzene, when there is a treatment of benzene with the succinic anhydride, there is a formation of this 3-benzoyl propanoic acid. So here it involves this Howard synthesis involves your 5 steps. So in your 5 steps, you will see the first step. In the first step, you will see that this benzene is reacting with this succinic anhydride, and there is a formation of this 3-benzoyl propanoic acid. After that, in the second step, you will see there is a treatment with amalgamated zinc to produce 4-phenylbutanoic acid. So this 4-phenylbutanoic acid is formed here, and in step 4, you will see that 4-phenylbutanoic acid is heated with concentrated sulfuric acid, and there is a formation of the tetralone ring closure reaction. So here you will see in the second step, you will see that this benzoyl propanoic acid is heated with this is treated with this zinc amalgam, and there is a production of this 4-phenyl butanoic acid, and this and in the step third, you will see the 4-phenyl butanoic acid is heated with your concentrated sulfuric acid, and there is a formation of this tetralone plus your H2O. Tetralone is a ring closer. Next, this tetralone is again heated. This tetralone is again heated with amalgamated zinc and HCl to give tetralone. So here, this tetralone, which is also known as 3,4-dihydro 2H naphthalene 1-one, this is treated with this zinc amalgam HCl, and there is a formation of this tetraline. This 1, 2, 3, 4 tetrahydronaphthalene is formed here, and tetraline is formed here. So in the step 5, tetraline is heated with palladium and palladium PD to yield naphthalene. So this tetraline is heated with this palladium, and there is a formation of this naphthalene. So this naphthalene is formed here. So reaction of naphthalene. The naphthalene is more reactive than benzene, and it undergoes several reactions like oxidation, reduction, addition, nitration, halogenation, and acylation. So there are 3 methods for the preparation of this naphthalene. First is your reaction in benzoyl. The first reaction is your benzoyl propanoic acid. Second is your from this phenyl-1-butene, and third is your Howard synthesis. Now the reaction, it is more reactive than your benzene, and it undergoes several reactions like oxidation, reduction, addition, nitration, halogenation, and acylation. So first is your oxidation. So in your oxidation, you will see here the naphthalene is treated with this naphthalene oxidizes. So here there is a formation of this phthalic acid in the presence of KMnO4 acidic media, and naphthalene is formed phthalonic acid by the KMnO4 reacting with KMnO4 in basic media, and when it is treated with this chromic acid, then there is a formation of this 1,4-naphthalene, and when it is oxidized with this ozone and zinc. In the presence of zinc and water, there is a formation of this dialdehyde. Next, naphthalene is reacted with this H2SO4 and H3SO4. There is a formation of this phthalic anhydride is formed. Next reaction is your reduction of naphthalene. So in the reduction of naphthalene, you will see this naphthalene, there is addition of this hydrogen atom, and there is a formation of this tetraline, and this tetraline is again hydrogenated in the presence of the nitrogen, and there is a formation of this decalene. After that, this naphthalene is treated with sodium methanol, then ethanol, then there is a formation of this 1,4-dihyperdile, and this naphthalene is treated with this hydrogenation is here. Then there is a formation of this decalene, and it is also forming a reaction with the sodium and this ester, and there is a formation of this tetraline is formed. Next, addition reaction. So there is an addition of bromine or chlorine to this naphthalene, and it gives naphthalene dibromide and or naphthalene dichloride. So here, if it is reacting with the bromide, then it will give the naphthalene dibromide, and if it is reacting with the dichloride, then it will give the dichloride. Further addition of this bromine or chloride result in the formation of the naphthalene tetrabromate or tetrachloride. So here you will see the naphthalene when treated with bromine, then there is a formation of 1,4-dibromonaphthalene. And after that, if it is again treated with bromine, there is a formation of 1,2,3,4-tetrabromonaphthalene. Electrophilic substitution reaction. So in this electrophilic substitution reaction, the naphthalene like benzene undergo electrophilic substitution reaction. Substitution occurs primarily at C1 alpha position, and this can be understood if we examine the intermediate carbonium ion is formed and two resonance forms are formed here. And there is only such form is possible for substitution at C2. So E1 is the in the following equation represent an electrophile. So here you will see there is an attack at C1 and there is a one substitution product is formed. So if attack is at C2, then there is a formation of two substitution product, and the former intermediate is more stable, and the product with the substitution at C1 predominate, and this beta position C at C2, the substitution that occurs at C2 that occurs only when the reaction is carried out at high temperature or when bulky or solvent are used. Nitration reaction. So in the nitration reaction, the naphthalene nitrate with a mixture of nitric acid, H2SO4 at low temperature, and there is a formation of this alpha nitronaphthalene. Halogenation reaction. So naphthalene when reacted with this chlorine halogen in the presence of iron catalyst, there is a formation of this alpha chloronaphthalein, and HCl and sulfonation of ethylene at low temperature or 80 degrees centigrade produces naphthalene 1-sulfonic acid, while at higher temperature 120 degrees centigrade it produces naphthalene 2-sulfonic acid. Here from this naphthalene at 80 degrees centigrade there is a formation of naphthalene 1-sulfonic acid, and naphthalene at 120 degrees centigrade there is a formation of this naphthalene 2-sulfonic acid. Now the questions. Which of the following molecule can act as molecular chaperone for assisting the folding of protein? That is your lipid. Which of the following macromolecule can be most successfully traversed among living whole? So that is your lipid. The enzyme abundantly distributed, that is your lipase. Naturally acting fats are L-type, and fats with unsaturated fatty acids are your solid liquid. And which among there is the simplest example for polycyclic arenes, that is your naphthalene, and arenes are polar. True or false, that is your B false. These are the references from where you can study this topic. Naphthalene or your polynuclear or aromatic hydrocarbon. Thank you so much for today's lecture.